Auzubillahiminash-shaytanir-rajim. Bismillahir-rahmanir-rahim. Assalamualaikum warahmatullah. Welcome to this short video lecture for experiment number 13 of our lab manual. So, as the objective suggests, in this experiment we are going to calculate various parameters of direct extrusion in the cold working process using some interactive simulation bench. So we are not going to discuss some details of what the extrusion is. We have already discussed these in our theory classes. For the brief overview, the direct extrusion is the extrusion in which the force is applied from one end and the part is squeezed out from the opposite end, and it is also known as the forward extrusion, while the other case is the backward extrusion in which force is applied from one side and the part is squeezed out from the same direction from the same opening. So we will jump towards the direct procedure. In the first point, you are given some links for the simulation bench here, and then there are some parameters that you have to select. So before going to the details, let's start with the simulation bench. So if you copy that link onto your browser, you will have this window on your screen. So we are going to perform the cold extrusion for this solid shaft with the die angle alpha of 45 degrees, and the die has no curvature. The friction of coefficient we will select to be medium, and the velocity of ramp, that is 1 millimeter per second, and as we have discussed, it will be the cold working operation. So let's start with this one. Once you have selected all the parameters, you will simply submit this details. So once you have submitted the details, you will have this video on your screen. I can just enlarge it. So this is the video of analysis software, that is ANSYS. Maybe some of you are familiar with it, and the extrusion is being performed on that software. So on the left hand side here you can see the strain values that are mentioned for various region of this work material. Let's suppose in this region the strain value correspond to this range, that is 3.58277, and at the bottom you can see a table between the length of the part in the container with the force that is being exerted, the force exerted on this edge, and the force is mentioned in tons, and the conversion for the tons into the newton is shown at the end of your practical. So what we will do, as you can see in your manual there, that you are supposed to calculate for two different lengths, that is 70 millimeter and the 50 millimeter. So we will just check out the value of the simulation software when the container length reaches 70 millimeter. So let it. You will just simply pause the video at length equal to 70 millimeter here. So you can see here at 70 millimeter length we have a force that is being exerted is approximately, each of this scale it corresponds to approximately 4 tons. So that would be around 123 tons around, right? So we know the force at length equal to 70 millimeter is 123 tons. So let's jump towards our calculations. So we'll just simply write down the force from the simulation software. The force exerted using a simulation bench is 123 tons, and you know let's convert it into the newtons. So it is 9806.65. that is the conversion rate for the tons into the newton. So that would be around, let me calculate this one, 123 into 9806.65, so it's 1,206,217.5 0.95 newtons. So this is the force at L is equal to 17 millimeter, as we have just seen in the simulation bench. Now there's some data that is given to us, and some data that is not given to us. So we will perform the hand calculations and we will verify that this value is either correct or not. So the initial diameter, as you can refer to your lab manual, we have the initial diameter of 60 millimeter and the final diameter of 30 millimeter. The diagonal is 45 degrees, and we have it's a solid shaft, and so on and so forth. And the material we are using here is the aluminum. So there are some certain properties for aluminum that we will take as a standard values. So just write it down. We will just simply enclose this. So we will first write down the data, that is we have initial diameter of 60 millimeter and the final diameter of 30 millimeter. We have the diagonal of 45 degrees, and the strain hardening exponent for the aluminum is 0.2, and the flow curve for the aluminum is 175 megapascal. So these two are the values for the aluminum material. If we select a different material, these values will change depending upon the material we are using. So the first and foremost, we in the extrusion process we calculate the extrusion ratio, and that is represented by the Rx, that is initial area by the final area. As we know, the area equals to pi d square by 4, the cross section area. So the pi and the 4 they will cancel out each other, so whatever remain is d naught square by df square. So we have 60 square by 30 square, and the value for the Rx would be 4. So this is our first value. Then the second, we have to calculate the true strain, that is epsilon and equals to ln of extrusion ratio, and that would be equals to ln of 4, and the value would be ln of 4 is 1.3862. So this is our second value. Then we have to calculate the extrusion strain here. So as given, the value of a and b is given in your manual, that is a equal to 0.8, b equals to 1.5. so we have a plus b ln of Rx, and we have 0.8 plus 1.5 into what is the ln of Rx, that is 1.3862. So it should be equals to 2.8793. so this is the value of extrusion strain, the value of extrusion strain here. Right, now we have to calculate the flow stress here, that is yf equals to k epsilon exponent n divided by 1 plus n. So we have 175. What is the true strain? We take this value as a true strain here. So 1.3862 exponent 0.2 divided by 1 plus n, so it would be 1.2, and that is equals to 155.675 megapascals. So this is the value of the flow stress here. Now another thing that we have to calculate is the pressure. If you refer to our previous details, as you can see here, and it is also mentioned in your lab manual as well, that in this simulation bench is assuming the friction between the work material and the die surface only. it is not taking into account the friction between the work material and this container surface. That is not being taken into account. Only the friction between the work surface and the die cavity and the die surface is taken into account. That's why we are using the extrusion strain, because when we use extrusion strain, it means we are assuming there's a friction between the work material and the die surface. And if we want to take into account the friction between the container and the work surface work material, then we have this additional value in the calculation of our pressure, and we have seen the derivation in during our theory classes. You can go back and refer to that value. So in this practical, we are not considering the friction between the work material and the container surface, so we are not going to take into account this additional factor in the calculation of our pressure. Let's discard this one. So we have the pressure that is just equals to flow stress. Let me write this one, equals to flow stress into the extrusion strain. Right, we are not taking into account as 2 value by T naught. So that would be equals to 155.675 into the extrusion strain, that is equals to 2.87 2.8793. So that should be equals to, let me calculate, 155.675 into 2.8793, 448.235, that is equals to 448.235 megapascal. So it is megapascal because we have the flow stress here and there is no unit for the strains. So this is the value for the pressure. Now using that pressure we are going to calculate the force. So the extrusion force, as we know, that is equals to the pressure onto the initial area. Why do we take the initial cross-section area? Because as we have seen in our lecture, that the force is being exerted on this initial diameter, right? It is not being exerted on the final diameter, so that's why we take the pressure that is being exerted on the initial diameter. So that should be equals to 448.235 into the initial area by d naught square, that is 60 square by 4. So by solving this one, we can have the force equals to 1,267,317.23 newtons. So this is our answer using the hand calculations. So we have just verified the results of the simulation using the hand calculations. As you can see, this whole calculation. So basically what's happening at the back end of this software, these equations are being run by the software, and what such software do, that if you see here, if you just see here, we have a chamber in that software like this one. Sorry for the poor figure, just for the demonstration, and we have a work material here. So what that software do, because applying these equation on the whole surface is not easy, so what that software do, that software divide the whole surface on the small chunks, regular shaped chunks, and it apply all these equation on each chunk. It will be applying all these equation on each of these chunks, and then it will accumulate, make an aggregate of all these results that is obtained from each chunks here, and it will give us the result. This is how this software work. So as you can see, we have just verified the value using the simulation bench from the hand calculations. So you can just repeat this value for at L equals to 50 millimeter, and you have to write down the values we have just find in this table here, and you have to show down the calculations in this section. And we have the conversion rates that are given here at the bottom, and at the end you have to answer this one and submit in the classroom. So that's all for this experiment. I hope you have a good understanding how we can cross check the simulation results using the hand calculation.